Hello everyone and welcome to the Rust Program Performance Optimization course. Today we will be talking about everything that is related to program optimization and getting things faster. So yeah, let's get started right away. This is going to be improv, and then I don't have a script. I'm just reading from titles and then explaining from the top of my head, okay? So yeah, what is optimization? What is optimization? What is our goal here? Heads up, I'm bad at explaining, so this is going to be sort of hard to follow, but yeah, it's gonna be like stream of consciousness kind of thing. So yeah, hopefully you guys are fine with that. So what is optimization? Optimization is when you want your code to run faster on the wall clock time, right? And maybe reduce your energy consumption, your memory use, your CPU use. For example, when I run cd-corn, let's go here. When I run this program, it takes a non-zero amount of time to compile and run, right? So I can try running, I can try timing that, and then it says the real time it took to execute was 18 milliseconds. Maybe your program takes 10 seconds to execute. Maybe it runs in an infinite loop, which is like a server, and then you have to optimize some other aspect of it, which is like handling an event. So optimization is the target of reducing that time or the energy use within your target machine, of course. They reduce the target energy use to get things running faster, use less resources, be more. It's basically just a feature. It's a good, cool addition, money saving. Yeah, it's all very good. It's all very good. So that is optimization. So let's get started. So one of the first things we need to talk about is how programs, what really programs are, how they're a transformation from source code to machine code and eventually executed by an executor. So when you have a program like this in Rust or any language really, this guide is mostly going to be program agnostic, but there are going to be programming language agnostic, but there are going to be parts that are Rust specific, such as LLVM. So programs are a transformation from source code to machine code. What does that mean? That means our source code is not the single layer, like not the single step when going from like code to CPU, what gets executed, okay? So if you actually go ahead and look at cd target, cd debug, we have our executable here, but we also have our deps here. This is the things that are used by the compiler to generate the final perf executable, which is being executed by the cargo run command over here. Let me clear the screen. Debug. And yeah, here's our executable. And we can do type perf, file perf. It says it's an ELF64-bit LSB PIE position-independent executable x86-64 target. Our target is x86-64 because I just compiled this for my own computer, and I'm running it on my own computer, which is an x86-64, as you can see from as you can see from here. I'm running on an x86-64 GNU Linux target. So your code gets compiled for a target. It gets interpreted by your CPU, which has a architecture and a microarchitecture extensions, and then you have your kernel and system calls, and then that kind of operating system level abstractions. So what you need to be aware of is that programs are not the only step. The source code to machine code transformation is not the only step when code is compiled. We're gonna touch upon those topics later. So second point, doing less is equal to faster. What does this mean? So I added a note here saying that it's not yanking out features. So what do I mean by doing less? So doing less is not really just removing code straight out from your program, like fn some feature that takes in a slice of commands and then executes the commands, like for command in slice and then command command.execute, something like this, right? And optimization is not just yanking out this feature and calling it a day. That is not optimization. What I really mean is, in some regard, you need to be thinking about, in some problem space, how do I do less work so that my program runs faster? Because optimization is all about doing less. So if I have a slice of commands over here, and I know that some of these commands might not really be need be executed, I can just, for example, before using this function somewhere else, like this, imagine I have some commands over here. Instead of running it directly like this, I could do let filtered commands, and then do some filtering on some previous command list, right? I have a command list, and I do filter command list, and then I pass in that filtered list of commands, so my some feature has a smaller subset of commands to execute. That is the kind of doing less I'm talking about. This doesn't just apply to filtering things, but also other contexts, basically, such as thinking more about your target, thinking more about your generated IR in LLVM, for example, stuff like that. Doing less is usually better, but that doesn't translate directly to code size, for example. Less code size doesn't necessarily mean faster code. That's why benchmarking and looking at the real results of your programs are really important. So that is the gist of this bullet point. So third point, LLVM optimizer, opt and optimization passes. In Rust, your program, was that a voice crack? In Rust, your program gets compiled, as I said, to medium intermediate representation, HIR, and typed HIR, and then finally getting passed into LLVM IR and LLVM, which does the actual optimization and compilation. So the LLVM optimizer, LLVM opt, over here, is the program that runs on the LLVM IR that the Rust generates, and then it uses transforms to transform that IR into other equivalent programs. That is exactly what's going on when we say the optimizer and the compiler is optimizing things. So a compiler doesn't really work like, oh, I have a program, I must immediately start both compiling and both optimizing at the same time. No, there are steps before we do actual compilation. LLVM IR is a representation of your program in the LLVM language. Basically, the IR is the language. There's also bitcode, but yeah, that's so optimizer runs on LLVM IR to transform code into equivalent other programs that preserve some sort of observability equivalence, and then like the transforms that are being made don't really change the outcome of the program, the observable outcome of the program. So within those constraints, the optimizer is allowed to do anything it wants. So how can we actually see this in action? So if we go to Godbolt, which is one of my favorite websites, actually, we can see over here that we have, where is it? Can I see the LLVM optimizer pipeline over here? Opt pipeline, yes. Here. We can view, where did that go? Oh, that's over here. What is happening? Why is it going over there? Anyway, error. Why is it giving error? That's interesting. That should not happen. An error occurred while generating optimizing pipeline. Invocation timed out. Okay, yeah, that's not really expected. If I do something like this, yeah, go back to the original. It's gonna fix it? Oh wait, I don't have a compiler. What happened to my compiler? Oh yeah, there it is. Can we finally see it? Yes. Okay, so we can see, just looking kind of scuffed. We can see the specific kinds of optimization passes that are being run over here. So every single optimization pass, it is being run. It's not changing the program. And here, some optimization happened. Why did my output just crash? What is happening? I don't really understand what is going on. Today's kind of scuffed. Please? I just want to view the optimizer. Please. Godbolt? You're not being helpful. This is my first time actually having problems with Godbolt ever in my life, by the way. Hello? Bro? Are you going to do anything? Can you compile it? It's compiling. Are Godbolt servers being hit by AI or something? What is going on? Why is it so slow? Well, I didn't have a backup plan for that, so yeah. But yeah, you saw that briefly, that we had passes on the left side here, and then on the right side we could actually see the LLVMIR that is being generated. And then when I switched to the green pass, that caused a change in the program, you could actually see some lines of code that have changed in the right side. You can actually rewind back and see what those changes actually were. So yeah, these optimization passes are defined in the LLVM source tree. If you go to the LLVM source, the Git, and this is probably a mirror of the LLVM Git. Maybe it's the official one, I don't know. And if we look into, where was it? There's like a folder that contains all of the optimization pipelines over here. Pipeline. Optimization passes, actually. MCA pipeline. Oh, MCA. We're going to talk about MCA later. We're definitely going to talk about MCA later. So if we go into, man, I really want to show you guys physically that where these optimization passes exist, and they're not like black boxes as we take them to be. Oh, where is it, man? That's so bad, like everything is just breaking. Anyway, we get the gist. LLVM uses opt. It is literally a program available in available when you have LLVM installed. You can see the usage here. It takes in LLVMIR and produces output. That's a huge help menu, dude. Please. Yes, opt LLVM bitcode optimizer and analysis printer. You can see what it's really doing in general options, and then specific options available over there. So yeah, LLVM, that's how it works. Fourth point, CPU architectures and extensions. So I talked about how your source code gets transformed into machine code, and that's how there's not only one step to it. So let's talk about the last step of this pipeline, this translation pipeline. Your CPU target, your architecture, as we saw, uname -A, it is x86-64 in this case. It might be something like ARM64 or ARch, LoonGarch, or some RISC-V based something, like a custom thing. I don't know, it could be everything. These CPU architectures, they actually determine what kind of machine code your CPU, the chip on your physical hardware machine, your motherboard, whether you're on a phone, whether you're on a laptop, whether you're on whatever IoT device you're on, that chip is capable of executing that architectural specification. In my case, it is x86-64, which is the most popular, basically every single computer, desktop computer, laptop, on the face of Earth, and gaming laptops, is this specification, x86-64. It's a very old specification, and by itself is actually very bare bones. What really makes it shine over here is the extensions that are built on top of it, which we're going to be talking right now. So this x86-64, the assembly output that we're seeing on this side, this is x86-64. All of these instructions and parameters, they're apparently, which syntax is this written in? This is Intel assembly syntax. So if you've never seen before, this is assembly. I don't really think this is your first time seeing assembly, but if it is, this is assembly, and assembly is a dump of machine code, which is just bits, zeros and ones, a stream of bits. So if you open a program, let's go back to the example over here. cd colon my development folder. You go into here, target, cd debug. So if you look at the binary of our program, this is hexadecimal, by the way. Hexadecimal is just another way of representing binary bits, zeros and ones, in a bigger symbol set. Instead of zeros and ones, so we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But instead of 10, we continue with A, B, C, D, E, F, which is 15. F is 15. And then we go into 1, 0, which is 10, but like it means 16. So this is hexadecimal. Each of these two letters makes a nibble, which is 4 bits. 4 bits, okay? Wait, no. Actually, each of these, one of these make a nibble, I think. Is that true? Is that actually true? A byte is 8 bits, a nibble is 4 bits. That means a byte has 256 alphabet size and nibble has 16 alphabet size. So that means a nibble is 1 hex character. Okay. Each of these characters is a nibble. And then a nibble is, as I said, an alphabet going from 0 to 9, and then A to F, and then looping back around to 1, 0, 1, 1, up to 1, 9, 1A, 1B, 1C, 1D, 1E, 1F, and then 2, 0, which is 32. Stuff like that. So when we dump the hexadecimal of our program over here, we can see that it is just zeros and ones like everything else in the program. So this is not actually, the computer just doesn't go and start executing from the first thing. If you go over here, the computer just doesn't just jump to the first address over here and start executing linearly. No. These executables are, as you can probably see here, are built into a format called ELF, or portable executable, or whatever executable format your platform supports. So this is the executable format that your operating system talks and understands, so it can load this program into memory and start executing it. We can analyze what these programs and how the structure of them work by using tools like OBJDump or LLVM OBJDump, whatever you have available in your system. And you can read all of the options over here to learn more about the sections like .text, .data, .rodata, .bss, the debug symbols, the dwarf symbols, stuff like that. All very interesting stuff. If you have time, you can ask AI about this to learn about this, but please don't make AI do your work. That's not the point of this video. I'm getting ADHD. So yeah, you can learn about all of these things. This is our compilation target. This is our compilation target. Here lives our instructions. Here are some of the strings. So yeah, this binary representation, it contains, some parts of it contains assembly, not assembly, machine code. And then when that machine code is interpreted, is about to be interpreted by a what am I talking about? Look, disassembly, okay? Disassembly. These nibbles and bytes, the CPU can understand these, but humans don't understand these, so we built disassemblers, which take these machine codes and convert them into assembly readable human format, which is debatably still unreadable, but much more easier to reason about for us humans and analyze. So this is the thing on the left you're seeing is an assembly instruction. This is what the CPU quote-unquote executes. There's a lot more rigor going on behind that, but we'll come back to that later. And these are the operands. So for x86-64, these instructions are specific to x86-64. I have, for example, these move or call. These are like very shared instructions between all the x86-64 implementations. But if I add C target CPU znver3 and specify a specific CPU, we can hopefully observe that the generated assembly changes. Because what we did over here, let's go back to the thing, we have changed our target CPU architecture and the extensions. We didn't really change our architecture. Our architecture is the same, but our microarchitecture and the extensions we allow on the specific CPU is vastly different. As you can see, we did not have these instructions before, and we got a lot more different instructions like vmove UPS. So it's a vector instruction. This is what you really want to see when you look at Godbolt outputs. If something is vectorized, auto-vectorized, or hand-vectorized, you will see a lot of these instructions, and they usually mean good things, packed singles. Really, really good. So that means that the compiler could optimize this really well. And then we have a lot of bit shifting and stuff and pointer access. General things you will see a lot, these sections, and then you will see these big sections where you have just a lot of instructions with V starting in front of them. So that's a good thing. By the way, don't judge the code I wrote here. I intentionally tried to trip up the optimizer here. Don't worry about what is actually going on over here. So yeah. So that is our target and our extensions. Let's talk more about slightly more about extensions. The specific extensions that I'm talking about over here are SSE, SSE2, AVX, AVX2, BMI2, FMA, stuff like that. SAD instructions. You can read the Wikipedia pages. There's a lot of sources available everywhere. For example, for GCC, you specify the CPU type and therefore the extensions with -march. For Rust, you specify this on the command line via, let's go back, either cargo run, before cargo run, you have Rust flags, which you specify your -C target CPU native or some other target CPU. But the one you'll be using most for development performance is native. And -C is a compiler flag, and target CPU is the flag name, equals native is the value for the key. So yeah, that's how it works. If I run this, it's recompiled the program for my specific CPU. And now this is running with specific instructions for my CPU. So there's that. Next, Godbolt, LLVM, MCA, and perf. So Godbolt, as we touched upon before, is the very good website. Every single day I use this. Make this a core part of your optimization basis here, and paste your code and look at the assembly output. There's a lot more resources on how to use Godbolt the best, but it's a very intuitive thing. You select your compiler here, and then if there's no compiler on the right side, you click here, add new compiler. You get a compiler. You drag this guy over here. You select your compiler version. There's a lot of compilers available over here. I usually use RedC Nightly because it gives least headache. You pass your Rust flags or similar things as we did here over here. C target CPU native, or other unstable flags like Z location detail none, stuff like that. You can do that definitely. But yeah, C target CPU. You can also specify your optimization level, like optimization level 3. But don't use native here because the server hardware, it's giving me a warning here. Native is not recommended because might change based on server hardware. So you can look at your rust up, the print, really forgot what it was. Print and let's see. Target CPUs. You can see our default architecture for that. And target features, was it that? No. Let's see. It's gonna take a little bit of time for me to go through. Info maybe one of. Okay, rust C print CPU stats. Please target CPUs, print CPUs that are not being used. Man, it is so hard to remember all these CLI flags. Anyway, so yeah, you can see a lot of things here. What was I doing? I forgot. I genuinely forgot what I was doing. Yeah, make Godbolt part of your daily routine. Very good thing to use. So target CPU, we can do ZNware2. That's my CPU right now on this computer. And LLVM MCA, it is available on Godbolt. Actually, you can add new or add tool LLVM MCA. We will get to this later when we are analyzing the let's see, what was the thing? Dash LLVM MCA deer flag. Timeline flag. Was it just timeline? When we're analyzing the... Yes, it is timeline. When we're analyzing the CPU instruction timeline, basically, we will come back to this later. But yeah, LLVM MCA, this is actually also a very good, useful tool to see what is actually happening. And then perf is the tool that we use for runtime code instrumentation. Perf help. We use this in conjunction with Cargo Flame Graph over here to produce flame graphs that are analyzable and helps you pinpoint where you can optimize your things. So yeah, that is the high level overview of the thing, and that is already half an hour. So yeah, let's get to the next topic, the reality of the situation. We talked about all of these things already, how the lower level things are being done. Let's talk about the reality of the situation here. We don't really care about any of these when our goal is to optimize. We want results, fast, effective, and not really want to think about more things, right? So yeah, let's get started. Your budget within a frame in a game. So I'm assuming in this bullet point, I have assumed that you're working on a game and then you have a budget of 8 to 16 milliseconds of time. You have a lot of time to execute code, do logic, and finish your calculations to present your frame to the user. That is our goal, and we want to get this time as low as possible, or maybe it is currently at 100 milliseconds per frame and we want to get that number lower. So our budget over here is 8 to 16 milliseconds. Let's do a simple calculation. All modern CPUs are minimum 3 gigahertz, running at 3 gigahertz clock cycles per second. Was that correct terminology? Yeah, I think so. And then it has 4 to 8 cores, which means we can calculate the total compute capacity over here in terms of cycles per second, like this. 3 gigahertz, so it's 9 zeros per billion. And then let's say we have 4 cores, and then we have 2 threads per core, and then we're looking at what is this? 24 billion, right? 24 billion per second. So we need to divide this by 1000 to get per millisecond, and then we have 8 milliseconds. So we have 192 million cycles of budget. I need you to fathom this number. 192 million cycles. You know how much logic that is? When we have an instruction in Godbolt over here, we're looking at specific instructions. Usually what happens is that some of these instructions take multiple cycles to execute. Some of these instructions can be executed in parallel. So let's say these instructions all take 1 cycle, maybe. I mean, this is a call, it's likely not 1 cycle, but maybe these instructions all execute in 1 cycle, and that is also possible. So yeah, just to show you the order of magnitude this thing works on, it's either per instruction it takes a few cycles, or a few instructions take 1 cycle. So around that ballpark, yeah, 192 million cycles. What this means is that I can have roughly 192 million lines of instructions over here, and that is the amount of logic I can basically calculate per frame my budget. So imagine I had a program that is like 100 million lines of code, right? And then the compiler ran some optimizations on it and reduced the code size and whatnot, and then optimized it and everything. I still have, like, it's just so many instructions per freaking frame. We have so much things that we could be doing in those frames, and instead we are riddled with overheads of all sorts of kinds. So the thing we're aiming for here is fit some logic within this frame in a better way. So we can go ahead and analyze the Steam hardware survey. I'm going to connect this with the one of those hardware survey things pop up when you're using Steam one day. And collected for. So you can go over here at the Steam hardware survey and you can analyze the consumer hardware of today and actually what people are running. For example, 45% of gamers are running AMD CPUs. 54% of gamers are using Intel CPUs, for example, or DirectX version, DirectX 12, DirectX 11, DirectX 10. You can look at the versions over here and more specialize your software to cater for more specific users or your user base. So there is also video cards like NVIDIA, AMD, Intel, GPUs. There's number of CPUs, as I talked about. I assumed 4 in this case, but 8 and 6 is also very popular. 2 is very rare nowadays, apparently. Or 27% of people actually have more than 8 CPUs or other amounts of CPUs. That is a lot. That's a big number. Mac hardware ownership, I'm going to ignore that. VR headset, I'm going to ignore that. I've never built for those. So you can look at the system RAM amounts, Windows 11 64-bit. You can look at all these kinds of statistics. The most important thing for me in this page is here. Specific x86 64 extension list. So AVX 512 VN and I, it has 22% 22% of gamers have this extension, which means you can use this in your game, and 22% of your player base will actually benefit from it. Roughly speaking, this is all heuristics. It will all change based on your target audience, obviously. And then we have SHA for SHA-256 hash, maybe not 256, but like SHA hashes. 78% of people have that. Fused multiply addition, 95%. SSE2, which is basically assumed on every consumer hardware nowadays, is 98%. NTFS, I don't really know what that is. BMI2, it's probably about a file system. BMI2, bit shifting extensions, 95%, very good. AVX, very good, 97%. LHF, SAHF, it's about whatever, I forgot what it was, but yeah, 98% of CPUs could support it. SSE 4.2, 98%, I did not expect that. That is actually very high. SSE 4.8, 4.1, SSE 3, AES encryption, speedups, compare exchange 16B, and then AVX2, prefetch W, BMA1, all kinds of very cool stuff. You can look at the statistics over here, so you can more specialize into your target audience. We will talk about what really bottlenecks our programs in the next session, next topic. So yeah, data access latencies, cache hierarchy, memory disk. I don't know what this is. Let me read about this. What was I supposed to talk about in this section? This is probably supposed to be merged into one, but yeah. What really affects your program today is that we have a lot of overheads going on right now in our code, and it is not well optimized mostly because of the paradigms that we are using, or the compiler edge cases. Miscompilations are also a thing, but they're rare. Don't assume that. And yeah, there's a lot of things we need to consider when making optimized software. There's things like data access latencies, cache hierarchy, memory disk. We'll talk about this later. I will open this, but I will open a graph from the Andrew Kelly Data-Oriented Design Talk, and show you, was it this one? Show you a specific graph, this exact graph from the thumbnail.
Of doing math.
Yes, exactly. I already reviewed it before. So I want you to look at this graph. On the top, it says not all CPU operations are created equal. So what does that mean? When I talked about showing you instructions like move, compare, jump, things like that, they touch memory, okay? They obviously work with memory. They move data, they compare data, they write out data, they do calculations. Every single program does this under the hood, no matter what you're doing. So a simple register operation, such as within register to register. So that means RAX to RBX to RCX. Stuff like that. Within registers, operations are sub 1 cycle. They take sub 1 cycle, which means they can be instruction level parallelized. They can be executed at once, as I talked about in the Godbolt example. A memory write apparently takes around 1 cycles. I don't really know what that means. We'll get to that later. And bypass delay, switch between integer and floating point units, 0 to 3 cycles. I don't really think about this. Write branch of if. So we need to talk about branch prediction. We will get to that later, obviously. Prediction makes a correct guess. That's a 1 cycle. That takes 1 to 2 cycles. That is really fast. Floating point or vector addition, 1 to 3 cycles. You can see how this thing is going logarithmically more and more to the right side. On the leftmost side we have 1 cycle. To the right of it we have 10 cycles. To the right of it we have 100 cycles. To the right of it, we have 1,000 cycles. To the right of it, we have 10,000 cycles. To the right of it, we have 100,000 cycles. To the right of it, we have 1 million cycles. And remember, our budget is 8 milliseconds, 8 to 60 milliseconds, and we have 192 million cycles to work with here. So the most expensive thing on this list, thread context switch, it takes 10,000 to 1 million cycles. So that means you can you can at most afford about 192 thread context switches, about something like that. The worst case scenario. And there's a cool visualization on the bottom that shows distance which light travels while the operation is performed. So in the time that it takes for your CPU to do one register operation, light speed has traveled from the bottom left of your screen to the top right of your screen. That is how fast these operations are being made. So yeah, let's continue. Multiplication. Any multiplication that you see in your math code or whatever you're writing, it takes 1 to 7 to 4 cycles. That is data that is not in the registers but already present in the cache. It takes 3 to 4 cycles to read and load that data into the register. So a TLB miss, what this means is translation look aside buffer. What is a translation look aside buffer? Translation look aside buffer. You can look this up in Wikipedia, and it means is a memory cache that stores recent translations of virtual memory addresses. So pointers and references in languages Rust, like Rust, C, Zig, they all work on one principle. Physical memory and virtual memory are not the same. We don't really work on hardware memory directly. We instead go for the OS and request a pointer, and then that OS gives us a pointer which we can then use. That is how everything works. And this translation layer, which is supported by hardware within translation lookup, helps the CPU look up those translations faster, or in the case of a miss, TLB, where is it? TLB miss? Yeah, it is just a miss. In the case of a miss in that cache, it takes 7 to 21 seconds, not seconds, holy shit, cycles to calculate the physical address of that virtual pointer. That is the amount of time it takes to do the thing. So if you have a lot of different pointers in your code, that's going to be very slow compared to, say, a register operation, which can be ILP, instruction level parallelized. That is what that means. So L2 read, the second layer in the cache hierarchy, it takes, instead of 3 to 4 cycles, it takes 10 to 12 cycles. Still pretty fast compared to everything else. Wrong branch of if, branch misprediction. This is what everybody talks about when we say branch misprediction. So branch prediction hardware in the CPUs, they're very complex and sophisticated things, but they work really well. Nowadays they can predict branches even if you're taking them like yes, no, yes, no, yes, no, stuff like that. They can like pick up on those patterns basically. And that's a very good quality of branch prediction. People are doing, Intel and AMD are doing really good work towards improving these things, but eventually they will all fail because not all if branches evaluate to the same branch. Usually some other branch is called, and sometimes that is not being able to be predicted correctly, and that causes instead of 1 to 2 cycle latency on the right branch of it, it takes 10 to 20 cycles of latency. That's a 20 times slowdown in your program that you can expect. Floating point division, 10 to 40 cycles. That's like if you have a vector library and you are normalizing a vector, you are dividing the x and y components of your vector by some magnitude for normalizing it. And one of those divisions, each of these divisions, take 10 to 40 cycles to complete. So instead of doing a division, you can do two divisions. You can do one division, the reciprocal of a square root of your magnitude, which will be your division factor. What was I about to say? Forgot. Oh yeah, instead of doing two divisions, you can calculate the reciprocal 1 divided by that magnitude, and then multiply by that magnitude twice in order to avoid the division, the 40 cycle divisions. So instead of doing two divisions, you do one division and two multiplications, and multiplications are obviously faster over here. Integer float vector, it has 1 to 7 cycles instead of the floating point division, which is 10 to 40 cycles, which can be or cannot be faster under the circumstances. Circumcision. And you should always benchmark your code before applying any of the aforementioned or future mentioned things. Always profile your code. A 108-bit vector division takes 10 to 70 cycles. Atomics CAS, I don't know what CAS means, but atomics is a specific CPU feature that is used to bypass the write buffers, so there are not synchronization failures between multi-threaded programs. So doing that takes 15 to 30 cycles apparently. C function direct calls, like ABI stuff, I'm assuming. Indirect call. L3 read. L3 read, the last of the cache hierarchy. We had 3 to 4 cycles, 10 to 12 cycles. L3 read is the last of the caches. It is the biggest one. It's shared. It takes 30 to 70 cycles to read from the L3 cache. And then finally we have main RAM read. This is usually what most of our headaches are coming from. Main RAM read. It takes 100 to 150 cycles. When your program is dealing with a lot of heap allocations, when you're allocating a lot of vectors within your code, intermediate vectors for storing your data, or constantly stringifying like owned versions of your strings and putting them on the heap, this is the cost you're paying for having that nice little feature. So instead of referencing already existent code data, which is probably already in your cache, you are making a new allocation somewhere random in heap, and then putting your data inside that, which when you read that data, it'll take 100 to 150 cycles, which is very slow. That's compared to, say, L1 read. Assume your string is an L1, 3 to 4 cycles. That is 100 to 150 cycles, which is 50 times slower. So that is how people achieve like huge optimization margins by applying all of these delays, all of the optimizations that are based on reducing these delays into something smaller and getting those huge 100,000 times speedups. And then we have the most important of these, kernel call. So when you read a file from a file system, for example, you are having a kernel call. When you are having an I/O call, such as sockets, asynchronous programming usually interacts with a lot of sockets. As I said, files and thread context switches, like inter-thread stuff. those take all 1000 to 1500 cycles to do. That means you should avoid kernel calls as much as possible in hot code. You should only do them where performance doesn't matter. Store the result in somewhere in your user space in your program, and then reuse that later. There's also things like mmap, but we'll not get into that over here. But yeah, that's basically what this is about. Data access latencies. That is what is plaguing your program today, and we should be striving towards reducing those delays. I will actually take a break here to drink something. I'll concatenate this video. You guys probably won't even see that part, so I'll be back.